Hello and welcome. Great that you're interested in polyhedral computations, solving linear programs or solving multiple objective linear programs, or one of the other bullet points on this list here. In this video I will show you how to equip your Matlab or Octave distribution with our toolbox called bensolve tools. First thing you want to do is visit the webpage tools.bensolve.org. You will get on this page here and see a list of operations, functions and functionalities which are covered by the toolbox. The second step will be to move to the download section and download the zip file bt version number.zip. After that you unpack the file in a directory of your choice. Now we start Matlab and move in that directory. I stored the files in documents, now I move in there. That's all we have to do. Now you can start working with bensolve tools. To check if the installation is working, you can type in plot ball 3, which should plot the unit ball of the one norm, which it is doing. If you are using Octave, there is one step you need to perform before you can use the toolbox, which is the following. If you look into the directory, there is a file called makeoct.m. You should call this function makeoct before you use the toolbox, then you should be fine. Now one last important thing. If you want to use the functions of the toolbox without moving to the bensolve tools directory every time, for instance when you use it in your own program, which we strongly recommend, you may want to save the path, which you can do in the following way. You move to the set path option in your environment section, in the home section, choose add folder, and now the bensolve tools folder should be selected by default, and then you choose folder and save it. That's all. In the end you will be able to perform polyhedral computations easily in Matlab. To give you a taste what's possible, I will show you some examples. The first thing we'll want to do is to compute the Minkowski sum of a three-dimensional cube and a three-dimensional cross polytope. To do so, we will define P as the cube in dimension 3 and Q as the unit ball of the one norm in dimension 3. And to compute the Minkowski sum, which we will call R, we just use the plus operator, so P plus Q. And it will look somehow like this. You are of course not restricted to the use of the polyhedra constructed by our predefined functions as cube and ball. In fact, you can work with any polyhedron you wish. To show you how this works, I will construct a polyhedron, which is the convex hull of the 20 columns of this random matrix here. To do so, we set V as field of the structure wrap. And to finally construct the polyhedron, which we will call S, we call the function polyh. And then we can plot the polyhedron, which looks like this here. Finally, we want to work with the Cartesian product of the polyhedra R and S, which we will call cart. And this can be computed by using the colon operator as R colon S. Obviously this polyhedron here is in dimension 6, so we cannot plot it, but we can, for instance, solve an LP using this polyhedron as feasible region. Let's say we want to minimize the sum of the coordinates x1 up to x6 over the polyhedron cart. The vector corresponding to this objective function would be the vector of 1s in dimension 6, which we will call C, as usual for LPs. So to solve this LP, we just call the function LPSolve, giving it the objective function vector and the feasible region, which is cart, and it solves the problem. As you can see, the toolbox provides easy to use functions for coping with polyhedra. To find out more, we encourage you to watch the following videos or to visit the webpage we started from in this video and read the manual. Thank you for watching.